Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to cover pretty much everything you'll ever want to know about carbocations for your undergraduate organic chemistry courses. This includes stability considerations, resonance, rearrangements, and stereochemistry. Let's start simple. What is a carbocation? Well, I'm sure you already know this, but a carbocation means a positively charged carbon ion. Carbo for carbon, cat referring to positive, and ion meaning ion. Let's make it a little bit more practical and relevant to you rather than just the basic definition. Let's talk about this. Carbocations have 3 bonds and 6 valence electrons. This makes them electron deficient, positively charged electrophiles, meaning we're going to attack them with a nucleophile. Carbocations are highly unstable reactive intermediates, meaning you're pretty much not done when you have a carbocation. They are usually an intermediate in a much bigger reaction. Carbocations have trigonal planar molecular geometry, which is going to be important when we talk about the reactions, and they are sp2 hybridized and have an empty p orbital, which goes hand in hand with the fact that they are trigonal planar. Let's make this even more practical, because a lot of the times when you learn organic chemistry, you learn a bunch of random facts and you're like, so what? So how do we actually make this really practical? A carbocation is a signal that not only is your reaction likely incomplete, going back to that whole intermediate idea, but that you should start looking for resonance structures in the intermediate, carbocation rearrangements in the intermediate, and stereochemistry in the final products. So again, a carbocation should signal you these 3 things. What you're currently seeing on the screen is something I've talked about extensively in plenty of other organic chemistry videos that I've made. But it's a concept that I find that students don't fully grasp until they see this multiple times and see many different examples of it. What I'm referring to are the synonyms in organic chemistry for weak and for strong. So what does weak mean in organic chemistry? Weak means that something is less reactive. And it makes sense that if something is less reactive, we can say that it's more stable. However, making that instant connection between weak and stable is a difficult jump because in everyday language, weak and stable are opposites, but in chemistry, they're the same thing. The other synonym for this is delocalized, and what I'm referring to is a delocalization of charge or partial charge. This is relevant to carbocations because a carbocation, if we can spread out the positive charge, we're going to make the carbocation more stable because we've delocalized that charge. On the other side of things, we have strong. Strong means that something is more reactive, and if something's more reactive, that means that it's actually more unstable. And if we have a charge that is all located in one position, we say that charge is localized, and that means that it is stronger because it's more concentrated in one area and more likely to either be attacked or do the attacking. When it comes to carbocations, stability is one of the most important concepts that you can understand. When we refer to carbocation stability, we're typically referring to 2 things, hyperconjugation and resonance. We're going to look at hyperconjugation first. Hyperconjugation is probably a term you don't really need to know at the undergraduate level, in that much detail anyway. It refers to sigma bonds donating their electron density to adjacent empty p orbitals, thereby increasing their stability. So in this image, I have methyl, primary, secondary, and tertiary alkyl carbocations. And you can see that as we go from methyl all the way through to tertiary, we are increasing the stability of the carbocations. This is due to hyperconjugation. But since you don't need to know that term, let's actually simplify this. Here's what you actually need to know. First, R groups, also known as hydrocarbon chains or alkyl groups, so in other words, your methyls, ethyls, terbutyls, etc., R groups donate electron density. Second, donating electron density to a carbocation, or any other electron deficient region, delocalizes the positive charge, which of course, according to our synonyms, means that we're making that positive charge more stable. And third, the more R groups surrounding a carbocation, the more stable that carbocation becomes. Hence, regarding the stability of carbocations, methyl is less stable than primary, is less stable than secondary, which is less stable than tertiary. Now, when it comes to these carbocations, methyl carbocations and primary carbocations are so unstable that they pretty much never form. The second factor that we need to discuss when referring to carbocation stability is resonance. When a carbocation is located on a carbon adjacent to a double bond, such as in the allylic or benzylic positions represented in the top left and top right images respectively, the molecule will have resonance. Now, I must stress that the positive charge cannot be found on the carbon that is part of the double bond. It has to be adjacent to it. Anyway, resonance delocalizes the positive charge of the carbocation across a much larger region on the molecule. And again, delocalization increases stability. As was the case with the alkyl carbocations on the last slide, allylic carbocations and benzylic carbocations can be primary, secondary, and tertiary. Therefore, not only can we stabilize the allylic and benzylic carbocations through resonance, we can also stabilize them further through hyperconjugation. Benzylic carbocations are considered to have similar stability to equally substituted allylic carbocations, although most sources do have them as slightly more stable due to having more resonance structures. If you're looking at those resonance structures depicted in those images, and don't fully understand them, you may want to review my video, Organic Chemistry Essentials Resonance. Overall, when it comes to carbocation stability, both resonance and hyperconjugation are important. I've created this image here, which shows kind of a scale of increasing carbocation stability. To review, methyl and primary carbocations are generally too unstable to form. That's why they're shown all the way on the left. Secondary carbocations have about the same stability as primary allylic carbocations. When it comes to primary benzylic carbocations, I've seen some inconsistency across resources, but most of them suggest that they are slightly more stable than primary allylic carbocations and are either equally stable or slightly less stable than tertiary carbocations. After tertiary carbocations, stability increases predictably for secondary allylic, secondary benzylic, tertiary allylic, and tertiary benzylic, respectively. Now, most organic chemistry classes will not require you to know this level of detail. Some classes may even have their own ranking system that conflicts with this one. This image was compiled after consulting multiple sources. It's not based on quantitative data that I found anywhere, so again, use this as kind of a reference guide, but if you're in a class and they show something different than what I have depicted here, use what they have in your class. Now that we've talked about the stability of various carbocations, the next logical step is to talk about carbocation rearrangements. Carbocation rearrangements are based on the simple fact that carbocations tend to rearrange to form more stable carbocations. And this is done via 3 different methods, prioritized in the following order. First is a ring expansion. You can see an example of a ring expansion in the top right image. Next, we have the 1,2 hydride shift, shown in the bottom left. And third, we have the 1,2 methyl shift, shown in the bottom right. We'll review each of those 3 types of carbocation rearrangements in more detail shortly. However, I did want to make this important note. When a carbocation rearrangement will result in a more stable carbocation, it will typically occur at an incredibly high rate. However, minor products are still observed in reaction workups in varying yields, depending on reaction conditions, meaning that carbocation rearrangements don't occur 100% of the time. Most undergraduate organic chemistry courses and standardized tests, however, will expect that you always carry out a carbocation rearrangement when it is favorable, and will expect you to only show the major product, which is the one where the rearrangement occurred. As usual, pay attention to how your actual organic chemistry class is set up, as sometimes some classes may expect you to know, or at least be able to show, how to get to various minor and major products. While ring expansions get priority over 1,2-hydride and 1,2-methyl shifts, they are the most complicated of the carbocation rearrangements. So to start us off, we're going to talk about the 1,2-hydride shift first. 1,2-hydride shifts occur when a hydrogen on a carbon adjacent to the carbocation is transferred to the carbocation, moving the location of the positive charge to a more stable position. When evaluating whether you can do a hydride shift, look at all the carbons adjacent to the carbocation that have a hydrogen bonded to them and determine whether that adjacent carbon would be a more stable site for the carbocation. I know there was a lot of words, and sometimes that can be hard to follow when you're not familiar with the language of organic chemistry, so let's do a couple of examples to show you how this works. In our first example, we have a secondary carbocation. We're going to look at the carbons adjacent to that carbocation and determine if either of them have, 1, hydrogens bonded to them, and 2, would be a better location for the carbocation, in other words, a more stable location. So if we look at the carbon down in the bottom left, it does have 3 hydrogens bonded to it. However, if we move the carbocation to that location, it would be a primary carbocation, so that would not work. The other carbon has 2 methyl groups and 1 hydrogen bonded to it. And if we were to move the carbocation to that location, we would in fact get a tertiary carbocation, which is more stable. So the 1,2-hydride shift is going to occur in this situation. Using the same arrow pushing convention we use to show a movement of electrons, what we're going to do is we're going to draw an arrow from the bond between the carbon and the hydrogen over to the carbon that has the carbocation. When we do this, the hydrogen is going to be transferred over to that position. I'm going to keep representing that hydrogen in blue so we know which hydrogen got moved. That is going to leave behind a carbocation in the place that we moved the hydrogen from. So you can see now that the tertiary carbocation is created when we move that hydrogen over. In our second example, we have a tertiary carbocation. I'm going to circle the 3 adjacent carbons to that carbocation position. The 2 on the left would be bad locations to move the carbocation because they are primary positions. At first glance, moving the carbocation to the position on the right looks like a bad decision as well because that looks like a secondary position. However, if you pay more attention, you'll notice that it's actually an allelic position. And it looks like it might be a secondary allelic position. Upon further analysis, you'll realize that it's actually a tertiary allelic position due to the resonance. So that is, in fact, whether it's secondary or tertiary, going to be more stable than the tertiary non-allelic carbocation. So let's draw in one of the hydrogens in this position and carry out the 1,2-hydride shift to see what happens. Once again, the electrons are found between the carbon and hydrogen in that bond, so we draw the arrow from the bond over to the carbon. When we draw the resulting carbocation, this is what we get. When I show the resonance structure, we'll see that this is in fact a tertiary allelic carbocation. The resonance structure on the right clearly shows that tertiary carbocation in the allelic position, and the one on the left shows a secondary allelic carbocation. That means the structure on the right is actually going to be more stable, and that's why it is the more major contributor to the resonance hybrid. In our third example, once again, I'm going to circle the carbons that are adjacent to the carbocation. We have a secondary carbocation, so if we were to move that carbocation to the carbon to the right of it, it would stay secondary. So that's not going to be enough of a reason to do a 1,2-hydride shift. If we move it to the one on the left, however, what we're going to be doing is we're going to be moving the carbocation to the benzylic position. It's a secondary benzylic position, so that will in fact be a more stable position for that carbocation. So once again, let's draw in that hydrogen, and we are going to show what is going to happen when we do that 1,2 hydride shift. Once again, we're going to draw that arrow from the bond between the carbon and the hydrogen over to the carbocation. And when we do that, we will get our answer. Now you can see that the new placement of the carbocation is in that more stable secondary benzylic position. Now that we've talked about 1,2 hydride shifts, the discussion on 1,2 methyl shifts should be even easier. That's because 1,2 methyl shifts are pretty much the same thing, except we'll be moving an entire methyl group onto an adjacent carbon rather than just a hydrogen. When evaluating whether you can do a methyl shift, again, you're looking at the adjacent carbons next to the carbocation that have a methyl group, but no hydrogen bonded to them. That's because hydride shifts take priority over methyl shifts in almost all cases, so you'll be doing a hydride shift if there's a hydrogen located there. If there are no hydrogens, go ahead and do the methyl shift. In our first example, we have a secondary carbocation, and adjacent to that carbocation to the right, we have a carbon that is bonded to 3 methyl groups and no hydrogens. This looks like a perfect time to do a 1,2 methyl shift. So we're going to draw our arrow from the bond between those carbons over to that carbocation, and this is the result that we're going to get. You can see that the entire methyl group got moved over to where the original carbocation was, and our new carbocation is now on that right-hand carbon, and is tertiary, which is more stable than that secondary one. In our second example, we have a tertiary carbocation, but if we move one of the methyl groups on the adjacent carbon to the right, we can actually turn it into a tertiary allelic carbocation. So that's going to be the driving force of this 1,2 methyl shift. You can see the resulting product on the right, and I went ahead and showed the resonance structure for it as well. Unlike when we did the 1,2 hydride shift on the previous slide to get the allelic carbocation, in this example, immediately upon doing the 1,2 methyl shift, we already see the tertiary allelic position. That means that this one is going to be the major contributor to the resonance hybrid, whereas the one that depicts the carbocation in that primary allelic position will only be a minor contributor. By now, you should have a strong sense of what to do when doing 1,2 hydride and methyl shifts. So here we have a tertiary carbocation, and to the left of it, if we were to transfer over one of those methyl groups, we would end up with a tertiary benzylic carbocation, which of course is more stable. So let's go ahead and draw the arrow here and see what that looks like. And there you can see on the right that we do have a tertiary benzylic position, which is going to be more stable than the tertiary position. The last type of carbocation rearrangement we're going to discuss is the ring expansion. As I previously mentioned, the ring expansion is actually going to take priority over a 1,2 hydride and a 1,2 methyl shift. But I decided to cover them last because they're actually the most complicated to learn, even though once you see it, they're not actually that bad. The other reason I'm covering them last is because some organic chemistry courses in undergrad don't actually teach ring expansions, so if you're not expected to know what a ring expansion is, feel free to skip this part in the video. A ring expansion is a type of carbocation rearrangement that occurs to decrease the angle strain associated with small ring sizes. In order for a ring expansion to occur, the carbocation must be located on a carbon adjacent to the ring, not on a carbon on the ring itself. So you can see in these two examples, I have a cyclobutyl group attached to an ethyl, and the ethyl, that adjacent carbon to the cyclobutyl, has the carbocation, so we could do a ring expansion in this case. However, in this second example, the carbocation is found on the actual ring itself, so we're not going to be able to do a carbocation rearrangement in the form of a ring expansion for that one. Let's talk about which ring expansions will actually happen now. Cyclopropyls, or three-membered rings, typically will not expand to cyclobutyls. Cyclobutyls, which are the four-membered rings, however, will expand to cyclopentyls, the five-membered rings, and cyclopentyls, of course, will expand to the cyclohexyls, or the six-membered rings. Once you get to cyclohexyls and larger rings, typically these will not expand. And the reason why a cyclohexyl will not expand is because it already is going to have that ideal bond angle. So adding extra carbons actually makes the ring more unstable. So if we look at these two examples here, I have a five-membered ring expanding to a six-membered ring. However, you cannot do a six-membered ring expanding to a seven-membered ring. Now, this may come up whether a cyclopropyl will or will not expand. A cyclopropyl expansion technically can happen, but it isn't likely, and it will usually not result in a major product. And that is for reasons that are far more complicated than what is covered in undergraduate organic chemistry classes. Some textbooks and professors, however, still teach these as if they are typical, so be considerate of the expectations in your particular class. Let's do a couple ring expansions to see how they actually work and how to draw them, because the drawing part is actually the trickiest part. In our first example, we have a cyclobutyl, and adjacent to the cyclobutyl, I do have a carbocation, so a ring expansion is likely to happen. Notice that's a secondary carbocation. You may be tempted to do a 1,2 methyl shift in this case, because a methyl is available to the left, and that would create a tertiary carbocation. However, remember that the ring expansion is typically going to get precedence over the 1,2 shifts. So before we actually show the arrow pushing, I'm going to go ahead and number the carbon at the carbocation with the 1, and then I'm simply going to go around the cyclobutyl with a 2, 3, 4, and 5. Next, I'm going to show the actual arrow pushing. Now, it doesn't matter if I take the electrons between the 2,3 bond or the 2,5 bond. So for simplicity, I'm just going to take it between the 2,5 bond. They are equivalent, so it really wouldn't matter. What I'm going to do is I'm going to take those electrons and draw the arrow to that carbocation. And I'm simply going to redraw everything exactly like it looks there, except the 2,5 bond no longer exists. And I have a new bond in this position right here. Now I'm going to go through and number exactly where I was before. So this was still the 1, and then we have the 2, the 3, the 4, and the 5. Now notice that the 2, we lost a bond between the 2 and the 5. The 5 got a bond back when it bonded to the 1, but the 2 is now electron deficient. So I'm going to go ahead and actually draw my carbocation at that 2 position, because that is the carbon that lost a bond. Now, this is really ugly. So what we're going to do is we're actually going to redraw this with a 5-membered ring and clean it up a little bit. So we're simply redrawing, and now I know I have a 5-membered ring. So let's go ahead and draw a 5-membered ring. And we can go ahead and number this ring as well, just so we can keep track of where we were. And it doesn't really matter where we start, because the numbering is going to tell us where everything else is located. So, at the 1, what is the 1 bonded to? Well, the 1 is bonded to this methyl group here. So we're going to go ahead and draw a methyl group at that 1 position. At the 2, we also have a methyl group bonded to that. So we're going to draw a methyl group at that 2 position as well. And notice at that 2 position, that is also where we have the carbocation. So we're going to put the carbocation right at that 2, and that is how we're representing the ring expansion in this example. In our second example, we have a 5-membered ring adjacent to a carbocation outside the ring, so this looks like another good time to do a ring expansion. Once again, I'm going to number the carbocation with the number 1, and then I'm going to go around the ring with the 2, 3, 4, 5, and 6. And once again, It doesn't matter if I take the 2,3 bond or the 2,6 bond, so I'm just going to take the 2,6 bond and I'm going to draw an arrow from that bond to that carbon where the carbocation is located. Again, now I'm simply going to redraw this exactly how it looks. But again, I am ignoring the 2,6 bond because we just broke it. So the 2 is still bonded to this 1 over here, but also the 6 is bonded to that 1 over in that position, and we still have a methyl group on the end here. Notice that the 2, let me renumber these, the 2 is where we lost our bond, and the 6 lost a bond but gained another one. So once again, we're going to put that carbocation at that 2 position. Now we're simply going to redraw this and clean it up so it actually looks like a 6-membered ring that we're used to. So there's our 6-membered ring, and we can number this however we want. Let's do 1, 2, 3, 4, 5, 6, and notice that at the 1, we have this methyl group here, so we're going to go ahead and draw that methyl group. And then at the 2, that's where we have our carbocation. Now, I'm going to put an asterisk next to this structure because we might not be done with our carbocation rearrangements. If you look at that carbocation product on the right, notice that we have a secondary carbocation. And if we look at that 1 carbon where we have that methyl group, there is both a methyl group and a hydrogen at that 1 position. If we did a 1,2 hydride shift now, that would actually move the carbocation to a more stable tertiary position. So the question is, can this occur after we already did a ring expansion? And the answer is, yes, it can. In fact, multiple rearrangements can be done in other cases as well. However, if multiple rearrangements are done, more minor products will inevitably be produced along the way. Some organic chemistry classes, I feel like a broken record saying this, will specify whether to carry out multiple rearrangements or to stop after the first. So again, be considerate of the expectations set forth in your particular class. All right, we've talked about the stability of various carbocations, and we've talked about what to do with carbocation intermediates when it's possible to form a more stable carbocation. Now we have to talk about what happens at the very end, because the carbocation, as I mentioned earlier, is not the end product. It is in fact just an intermediate. And this is where we have to pay attention to stereochemistry. Stereochemistry is something that scares a lot of students, and that's usually because they never quite learn it the right way the first time around. Now, if you want a more in-depth lecture on stereochemistry, feel free to check out my Organic Chemistry Essentials video on stereochemistry. To help you understand stereochemistry of carbocations, I'm using both pictures of 3D models as well as flat drawings. Now, if you look at all 4 of those 3D models and all 4 of those flat drawings, you might realize that they are all representations of the same exact carbocation. The central atom in a carbocation does not have stereochemistry, and that's because it's trigonal planar and there are only 3 groups attached to it. You need 4 groups for something to be considered a stereogenic center and to have stereochemistry. Each of these depictions can simply be flipped or rotated to appear in any other of the orientations. So go ahead and look at those and see, okay, I can just flip this one over 180 degrees, or flip it left to right, flip it top to bottom, or just rotate it, and we'll arrive at any of those other representations. So in other words, they are all identical. Now I also wanted to show you the side view of a trigonal planar carbocation, because when we view it from the side and not from the top, it's easy to see the planar component of the trigonal planar molecular geometry. In other words, it's flat. Not only that, but a carbocation on that central carbon has an empty p orbital that extends above and below the plane of that carbon. Lone pairs from nucleophiles can attack that empty p orbital from either side, either that top side or that bottom side, with equal probability, which is why we have to pay attention to stereochemistry when dealing with carbocations, at least when there's 3 different groups attached to that carbocation. So hopefully in that depiction on the bottom right, it's easy to see, okay, I can attack from above or below because I do have that empty p orbital. In order to illustrate these stereochemical considerations with carbocations, I want you to pay attention to this model that I have. I have a trigonal planar carbocation on the left of the reaction arrow, and on the bottom representation, all I did was flip it 180 degrees from top to bottom. So again, I have the same exact carbocation on the top and on the bottom. What we're going to do is we're going to take a nucleophile, and we're going to attack it from above in both of these representations. This is going to result in enantiomers. So if you look at the products on the right, you can see that we actually have a mirror plane between them that shows that they're non-superimposable mirror images. We can attack with equal probability from both sides, or we can view it as, if one molecule is upside down, we can attack from the same side. Either way, equal probability that both of these are going to happen, so we're going to get this racemic mix of enantiomers if we react that carbocation with a nucleophile. Now I have a drawn depiction on the right. In this depiction, I have a trigonal planar carbocation on the left, and it's oriented the same way on both the top and the bottom reactions. The difference between these is that I'm showing the nucleophile attacking from the top side in the top one and from the bottom side in the bottom one. And again, both of these situations are equally likely, resulting in a racemic mix of enantiomers that are shown on the right. So in other words, anytime you're dealing with a carbocation intermediate, and there are 3 different groups on it, and we're attacking with a 4th unique group, we're going to get multiple products in the form of enantiomers in this case, and in other cases, you'll just have to look at the rest of the molecule to determine what they are. But at the actual carbocation location, you're going to get a mix of adding from the top and adding from the bottom. Now, just a quick note, with molecular modeling kits, different colors do represent specific atoms. In this depiction, on that top left though, the different colors, they're just simply meant to represent different groups, not any particular atom. The white atom is only meant to represent a generic nucleophile in that depiction. So anyway, when you're dealing with carbocations, in summary, you have to worry about the stability of the carbocations. You have to make sure you're checking for those carbocation rearrangements, those 3 types we talked about. And then before you move on to the final product with whatever reaction you're doing, you have to pay attention to stereochemistry. Now, all of this recap seems like a lot. However, I have a video called the Organic Chemistry Problem-Solving Process, and it goes over how to handle reactions from front to end, and it guarantees, if you follow it, that you don't miss these things along the way. So, as you start getting more and more into reactions, please check out that video, and it'll help you out quite a bit. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.